real briefly, what I'm going to try to cover today, quick intro. I do see, even amongst this blinding light, I do see a lot of familiar faces. A lot of you are familiar with Loomis, but those who aren't, we'll give a brief intro. We will also briefly discuss some of the major hardware challenges that we see, especially on the optics side, in terms of bringing AR to the mass market, to the mass consumer market. We're going to talk how Loomis conveniently checks all the boxes to provide such a solution. And we're going to get into the manufacturability of the Loomis waveguide. In fact, the reason why I accepted Bernard's invitation to speak is, I think in general we have a pretty good position in terms of leadership when it comes to optical performance, but there has been skepticism out there and a lot of questions I keep answering when people ask about the scalability of the technology. So we're going to address that head on today. So brief intro to who we are. Loomis was founded in 2000, specifically we're an optics company. The company was founded based on a major breakthrough in near-to-eye display based on our reflective technology. We position ourselves not to be the end product, not to make the full AR glasses, but rather to have the core enabling technology, that key core enabling component. We call it the Loomis inside, kind of like the Intel inside. Looking at you, Ron. I know, but it's a good ingredient branding in terms of positioning. So that's really where we see ourselves. We're really good at optics. It's definitely a category where companies have major bottlenecks in resolving, especially when it comes to AR display. So if we play this right, we become the key enabler to most of the tier ones, if not all of the tier ones in the market. Part of our age, the fact that we're nearly 2 decades old, is actually a massive advantage for us. I think we've heard multiple times, I think Jerry kicked everything off with there's no free lunch, there's no Moore's Law when it comes to near-to-eye display optics. I know I'm very much preaching to the choir. And that's why the fact that we've been around so long, bashing our heads against the wall, trying to solve really difficult physics issues and challenges is a huge advantage. And we're at a point where basically, most of the, I would say, practically all of the major engineering challenges of taking our technology to mass consumer are safely behind us. Another advantage of our age is we're able to get into a very unique IP position that protects our novel reflective waveguide technology. It has protected us many years and has enabled us to continue building off that and continuing the innovation and extending that patent portfolio, which gives us still another 2 decades and then some, so don't get any crazy ideas. We're shipping. We've been shipping for several years, starting off with the professional applications. Most notable, we have the US Air Force using it on the A-10 of the F-16s. We actually sell that through partnership. We sell that to Thales. Thales sells that into, Thales Visionics sells that into the US Air Force. Other applications that we've been shipping, as we mentioned, other professional applications. Daiquiri's using it in their smart helmet. Suncorp in Japan is using it for automotive assembly. Augmedix is using it for spinal surgery, so you're talking about real AR assisting doctors, making it safer for the patient and enabling the doctors to bill more patients faster. Quake Technologies using it for firefighters to help them see through smoke. So again, another life-saving application. In terms of production, we do have an in-house production line that was established in Israel several years ago. We've shipped tens of thousands of units from our home base. And we also announced a partnership with Quanta about 1.5 years ago, Quanta Computer in Taiwan. And their production line has already started underway this past year with major ramp up expected over the course of this year. And that partnership was extremely critical to help us really meet the need of this consumer market that we see happening, we see swelling up. So, as I mentioned, consumer market, we start to feel it's happening. We see the billions of dollars of investment from these companies. A lot of the guys in the crowd here are working for those companies, futzing around with those big budgets, also bashing their heads into walls trying to resolve very hard issues. Among the hardest issues is specifically in the hardware and specifically in the optics. And when we think of the optics, the optical display challenges, we put it in 3 categories: performance, cost, and form factor. So if we go through performance, we look at key parameters like field of view. You want to have a large enough, meaningful enough image. Again, depending on the application, sometimes 10 degrees, 15 degrees is okay. But the consumer market wants more. They want something large, meaningful, and immersive. So field of view definitely has to be usable for these applications. You are asking consumers to change their behavior and start wearing a new device, start plugging in a new device every night. And therefore, that's going to have a use to it. So field of view is actually very important to check that box. Optical resolution. We're used to these amazing screens in our pockets, on our desktops, and in our homes. So when we look at displays, we want to be able to actually read documents, read internet pages, especially when you look at the first initial consumer applications. There's a bit of a prosumer application where people are using it for extended desktops, etc. So optical resolution is very important. Color uniformity. I know that's a very sensitive issue to the diffractive crowd here, but sorry guys, it's a big deal. And like I said, people are going to be looking at documents, internet pages. No offense, guys. You want to see a slide like this. You want to see it completely white. You don't want to see this rainbowing, rolling effect. Brightness. That's another big one. That's one where actually I'd say at least 90% of the solutions out there fail. And we're talking about devices that are going to be mobile. And mobility, by definition, is your customer, the consumer, is going to be everywhere. And you cannot control the fact that hopefully he'll be outside and using these devices. He'll be in rooms where he's got sunlight pouring in. So brightness is a major parameter that needs to be taken care of. Alongside with that is power consumption, power efficiency. So the brightness efficiency, you might come with some diffractive waveguide where you could really jack up the brightness, but if you burn through the battery within 10 minutes, you essentially gave the consumer a useless product. Then, of course, there's the things that keep all the physicists up at night, the various optical artifacts that need to be designed out. Certain technologies lend themselves to really have all these artifacts, both from the outside worlds, if you think about the varying rainbow effects that you get with diffractive, and all types of ghosts and stray lights and all those good things. Cost. This is going to the mass consumer. When we talk about mass consumer, we're talking about tens of millions of consumers. Maybe not next year, but hopefully in the next several years we'll get there. And in order to be there, you're going to have to hit certain price points that, basically the end device is going to have to be around the cost of smartphones. High-end smartphones for higher-end products, lower-end smartphone pricing for lower-end AR products. But that's more or less where we are. So no matter how much we say we are key enabling components, we are components at the end of the day. And when it comes down to the strip down of the bill of materials, we have to make sure that the technology is priced accordingly. Then last but not least, form factor. A lot of people have mentioned it throughout the various talks. This is for consumers who have to put this on their face. We say at home, the face is a sacred space. People, you could check off the first couple boxes. It's cheap enough, great performance, great capabilities. But if the consumer looks like a total dork, he ain't leaving the house with it, and therefore, you're not really going to get that many customers buying it. Other challenges not to be belittled, on the software side, on the other hardware side, and SLAM Technologies, interface, killer application. That's a big open question, and a lot of different answers you get. Obviously, those are major challenges, and those are being dealt with. But if we had to crystallize where the single biggest bottleneck is, it really is in the optics hardware. And like I said, I feel like I'm preaching to the choir here. So, enter the Lummus solution. So Lummus, we basically design what we call optical engines. The optical engine is comprised of 2 components. First, you have a projection module. Think of it as a pico projector, projects the image into the waveguide, the second component. The waveguide is where we have really a core differentiator, the fact that we're reflective. So the way it works is we project the image into the waveguide. The image is trapped through total internal reflection. it travels till it gets to an array of partial reflectors, and the partial reflectors recombine the image. They fan out the image in front of the eye, giving a large field of view, a large eye motion box, and a clean, crisp, coherent image to the wearer. Here is another angle, top view angle, more of a diagram of the way the waveguide works. As you can see, the image is coupled in from the edge. The light travels till it hits the array of partial reflectors. And you can think of the partial reflectors as basically, instead of having one big fat beam splitter like you have with the Google Glass, where you have this big trade-off in terms of the larger the virtual image, the larger the bulk of the optic in front of the eye. Essentially, what we're doing is, instead of one fat beam splitter, we're giving you an array of beam splitters. We're cutting it that way, so you could have it thin, less than 2 millimeters in terms of thickness, so we could enable true wearable form factors while having a meaningful field of view and large eye motion box. So some key waveguide features. If anybody recognizes this awesome test pattern, you could download it yourself for free from Carl Guttag's website. This is an awesome test pattern. We love it because it really shows the difference between a high-quality image and not such a high-quality image. When you have issues with color uniformity, you have issues with sharpness, the ability to read letters. That's where everything really, really sticks out. So as we mentioned, Loomis pretty much checks the boxes on all the core parameters that are really important to having a meaningful, useful, near-to-eye display. So in terms of the field of view, the eye motion box, very high optical resolution. I'm looking again at the test pattern. I'm like, we love this so much that we actually use this in our demos, and we tell anyone out there, go compare the competition, use the same exact test pattern. In fact, that's what Carl did on his website. True see-through, so the fact that we're not causing any kind of distortion in your view of the physical world, we're not causing any dimming in your view of the physical world. That's something that's very important. The high brightness, as Jim could attest to, this is being used by the Air Force. Everyone's flying above the clouds. Every day is a sunny day, and our waveguide display holds up to extremely bright scenarios. Of course, that also goes hand in hand, as I mentioned, with power efficiency, and that is going to be critical for a consumer product. It's clean, crisp image, artifact-free. We don't get those elements that fly in there from ambient light or inherent strays and ghosts that you get with other waveguide technologies. Consumer-friendly price point, and we're about to get to that, and of course, enabling a slim, wearable form factor. So I didn't come here to tout, or make the case why our waveguide outperforms other technologies that's out there. This is in general an industry consensus. Anybody who's done side-by-side comparisons, it's been conducted online by disinterested third parties. I've heard it from many of you actually in the crowd who have actually seen the various solutions and conducted side-by-sides, especially with challenging test patterns. That is the fact. We're not coming to convince anyone. The one issue that keeps coming up is people keep thinking that our technology has this exotic waveguide, so is it really scalable? So the answer, of course, is yes. But we're going to go a level deeper, and actually, for the first time in Loomis history, we're going to open the kimono and explain how we make these waveguides to help bridge the gap of understanding and bring you on our side. So we're going to go into how is it made. Everything starts with plates of glass. Hold the plate of glass in my hand. And just for clarity, all these plates of glass that you see here, that's all glass. To make it easier to follow, the coated glass is in yellow. The uncoated glass is in gray. So it starts with a simple piece of glass, plate of glass, that we get from a variety of manufacturers. Very easy to achieve. No, crazy exotic refractive index. In this case, it's BK7. Very, very simple, very achievable. No problems when we get it, hand delivered, delivered in trucks. There's no issue in terms of flatness or anything like that. And what we do is we put it through a coater. The coater is part of our secret Coca-Cola recipe. It's standard coating materials. Obviously, we don't like to say the exact ingredients how we're doing it because we don't want to make it too easy for people to copy us. But these coatings actually represent a partial reflector inside the waveguide. So you put these through a massive coating machine, so you have these drums that it could actually hold hundreds of pieces in it. And the next step in the process is you stack these coated plates. On the top and bottom, the bigger slabs are actually the uncoated slabs. And then you could actually see over here, we denoted where we do the slicing. The stacking is also a very simple process, very standard process, the process that's been used for beam splitters for over 100 years. We'd use off-the-shelf optical adhesives. And we use various vendors for it. We create our own recipes, but not rocket science in terms of how we do that. Standard stacking process, and then this goes through a slicing process. We use wafer slicers, the same used in semiconductor. So everything we're doing here is using standard materials, standard processes, standard machineries. No materials being used here have not been used for the last 100 years. Everything has been around for a very long time. Very straightforward. So we take this, we get a bunch of slices out of it. Slice comes out like such. This is a slice. I don't know if you can tell through the lighting. There's actually the facets, the partial reflectors already here. It comes out a little foggy, so we put it through a lap and polish machine, which brings it down to a nice, clean optical grade. Very simple process, very standard process. Once again, standard machinery. And they come out looking like that. Then we just slice them. In many cases, we slice them in half, so you get 2 waveguides out of them, and we shape it for the particular shape of the eyewear that we're going to be selling it to. And like I said, standard equipment. So we're looking at standard coating machines, a very standard stacking process, slicing, off the shelf. Every bit of machinery, lap and polish, shaping, testing, all off the shelf processes, all off the shelf machinery. In fact, these could be outsourced at a variety of places. Let's go a level deeper. Let's talk money, because at the end of the day, it's for consumer. The whole case here we're making is about cost. Are we getting the cost down? So what we did in this little experiment, what we did here is we took our Vision product, which many of you have seen. We've been showing it. We showed it at CES. We showed it next door. This is our flagship product. And we took that particular waveguide using BK7 glass. And we did the cost modeling. At 100,000 waveguides per month, so that's 50,000 pairs per month, and that's an entry-level consumer market quantity. Ultimately, we'd like to see that number go up to millions, but as we transition, you're going to have a few 100,000 units in the market as you bridge that. But already at that point, we need to make sure that we're hitting consumer pricing. So we take that number, we take all those processes we mentioned, coating, stacking, slicing, lapping, polishing, shaping, testing, and we factored in yield, and the yields are high, and the yields are very repeatable. Again, mentioning we use raw material that's just simply off-the-shelf glass, and factoring all that overhead, factoring all the entire cost, it's the raw material cost plus $3. That's it. Surprising? It's a lot simpler. What's the raw material? Where's Rudiger? He'll give you a quote right here on the spot. And if this little bit doesn't convince you, I'd say we have a handful of copycats on the other side of the world. Do you think that they'd be copying it if this was an extremely expensive process? I rest my case. So, brief summary, and we'll leave you with a lasting image. So, we are best in class. We are the benchmark when it comes to optical performance. It is mass manufacturable. I would challenge the other waveguide manufacturers to come up here and show their breakdown and their BOM, how they get to their pricing in mass consumer. And the lasting image I want to leave here is what we have coming next. We're doing some major breakthroughs on 2-axis expansion, which enable us to significantly shrink the form factor to get it super low and natural looking. It's going to be starting with over 50 degrees. We have a roadmap that gets that to 70 plus. Once you get them small enough, you can start getting really jiggy with it and cascading the waveguides, especially when they're cheap enough. And you could start imagining how you get to 150 degrees as well. And if you want to know what we're doing on 2-axis expansion, ask this kind gentleman to invite me back next year.
OK, thank you, Eric.
I'm good.
Thank you.